So the Harsha will make a small presentation of 45 minutes, after which I will give the virtual floor to the reviewers first. And I think going from the furthest away, RS, then to Paul, then to Jimedo, and then to the examiners, Shamita and Michel and RS. RS first, actually, because he's the furthest away, then Shamita, then Michel. And so I will briefly present the jury. Harsha, so we are here gathered virtually and in the room of INS for your diplôme d'habilitation à diriger des recherches, for which you will give a presentation today and we will have a discussion afterwards. So the title of your HDR is Supérieure Earthquakes. And the reviewers are sorry, sorry, they are, but no. So there is sorry, Jimedo Kondo, who is professor at the Sorbonne University, Paul Johnson, who is lead research scientist at Los Alamos, and Michel Bouchon, who is directeur de recherche émérite à l'Université de Grenoble-Alpes. And the three examiners are Shamita Das, professor emeritus at Oxford University, RS, professor at the California Institute of Technology in Los Angeles, in Pasadena. And sorry, I'm getting lost in
that's
my.
It.
And that's it, actually, and me. I know, and me. And me. I am Alexandre Chudel and director de recherche here at INS. So, Harsha, after this long introduction, a bit confused, please, we're most happy to listen to you.
Okay. Yeah, no, it's all good. All right. Well, I was talking about the classical view of an earthquake, where plates try to slide past each other around faults, but faults resist its motion due to friction. Because of this, there's a buildup of energy in the medium that's hosting the fault, and it increases the stresses on the fault. And once these stresses exceed a frictional resistance, the plates slide past each other and the fault ruptures or unzips. And this leads to a sudden release of this stored energy called an earthquake. So one important concept to keep in mind is how fast this unzipping occurs, or the notion of a rupture speed. So as the fault ruptures, it radiates two types of body waves into the medium: pressure waves and shear waves, or P waves and S waves. And thus three different speeds come into play. We have the rupture speed, we have the S wave speed, which is of the order of 3.5 kilometers per second. And we have the fastest wave, the P wave speed, of the order of 5 kilometers per second. And we know that a vast majority of earthquakes have rupture speed slower than the S wave speed of the order of 2.5 to 3 kilometers per second. We call such class of earthquakes subshear earthquakes. The easiest way to visualize the three different speeds is to imagine a point object running along the line, sending out P waves and S waves. The P waves are in blue and the S waves are in green. And the fault is represented by the dotted line. And that little yellow triangle is the rupture front, and the speed at which it moves is what we call a rupture velocity. And it's clearly slower than the S wave speed. So this is an image you could keep in mind when you think about a subshear earthquake. However, occasionally, ruptures tend to go faster than the S wave speed. They're still slower than the P wave speed. And such class of earthquakes are called supershear earthquakes. And if we do the same exercise now for a supershear earthquake, several characteristic features emerge. One is that the rupture front is moving faster than the S wave speed. So two linear fronts emerge, and I'll talk more about them a bit later. But as you see, the rupture is still slower than the P wave speed. Now, the word super shear might remind some folks about supersonic. And if so, you got the analogy right. Supersonic is when bodies in fluid go faster than the speed of sound. And we normally associate supersonic with aircrafts. And you can see the image to the left of an actual aircraft, actually. This is not in a wind tunnel. And you see several linear fronts that develop, just like the two linear fronts that are developed in the image on the right. These are what we call shock fronts or Mach fronts, and they are named after Ernst Mach and fairly Peter Salcher as well, who did the first experiments on a bullet from a rifle propagating faster than the speed of sound. And they captured this in late 1800s, the image of a shock front. So now that we have established at least a general notion of super shear earthquakes, I'm going to restrict myself to talk about the work I have done in the past 13 odd years on super shear earthquake. So I will not be covering the entire topic of super shear earthquakes, and I'll be focusing just on the work done by me, my colleagues, and former students on this. So a quick run through on the theory of earthquake ruptures. We're going to focus on the part where earthquake ruptures are modeled as dynamic shear fractures. So Craggs in 60 first constructed a solution of a steady state semi-infinite crack. And he showed that a stable crack growth is possible if the energy from the medium is absorbed at the crack tip. And this is only possible if the rupture speed is slower than the Rayleigh wave speed. And we'll be clear about what is Rayleigh wave speed precisely a bit later. Kostrov in 64 developed a self-similar solution of a propagating shear crack and showed that this energy will actually be radiated out of the crack tip if the rupture speed lies between the Rayleigh and the shear wave speed, and hence it's forbidden. Thus, mode 2 shear cracks will tend to propagate in the sub-Rayleigh rupture speed regime. Vietman in 69 treated cracks as smeared out dislocations and used a velocity-dependent friction criterion, and said that super shear velocity is in fact forbidden for shear fractures. However, Burridge in 73, developing a solution for a self-similar mode 2 crack, showed how to bypass the forbidden speed regime by introducing a mechanism where a peak in shear stress propagates ahead of the crack front at the S wave speed, nucleating a second rupture that is by nature born super shear and then merges with the main rupture. We'll see this in more detail later. As far as I'm aware, Hamano in 74 provided numerical solution of a rupture propagation. I have access only to an AGU abstract, where he claimed that propagation velocity increases monotonically up to the P wave speed. Andrews in 76, this is probably the paper most people know about, numerically simulated the transition from sub-Rayleigh to super shear, the transition around across that red forbidden zone, and thus validated the Burridge mechanism. He also identified the mechanically stable portion of a super shear rupture speed regime. And he introduced the notion of a transition length, which is the distance a rupture has to travel before it transitions from sub-Rayleigh, sub-shear, if you like, to super shear. At the same time, Das 76, that's a thesis, and then Das and Aki 77 also numerically simulated sub-Rayleigh to super shear rupture transition, where they crucially introduced the S ratio. It's a non-dimensional measure of the strength of a fault, and showed that, along with Andrews as well, that for a particular value or range of S, you will get super shear rupture. So essentially a recipe to generate super shear ruptures. Burridge then went ahead a bit further, did stability analysis, and verified all the admissible speed regimes shown in green here. Friend then in 79 produced the solutions for stress and particle velocities due to a steady state shear crack, and also verified energetically the stability of sub-shear crack propagation. So, excuse me, I'm going to start off with Friend's solution because it's the easiest one to intuit and plot. And I'm going to start showing figures like this for a bit. So let me walk you through it. This is a solution of a 2D steady state, which means the crack is going at a constant velocity, a singular elastic fracture, which means the stresses are infinite at the tip of the crack. And crucially, it's sub-Rayleigh. The figure on the left shows the particle velocity field. The arrows show the instantaneous velocity vectors. And the two things to keep in mind here is that the particle velocity vector is pointing up, and that's normal to the fault, which is shown by the dashed black line. So we call this dominantly fault normal motion. The figure to the right says that this intense velocity field around the tip of the crack decays as the square root of distance from the tip of the crack. When we construct solutions for super shear ruptures, so ruptures going faster than the shear wave speed, again, if we focus on the figure on the left, it's showing the same thing, but the features look different. You first notice the emergence of two linear fronts. Those are the shock fronts. And you have a concentration around the tip of the fracture. The fault is still shown by the dashed black line. But strikingly, if you look at the velocity vectors, they are dominantly parallel to the fault. So we call them dominantly fault parallel motion associated with the super shear rupture. The other crucial thing is that the region encompassed within the two straight lines is a combination of shear and dilatational motion, but the region outside the linear fronts or the marked fronts is purely dilatational. In other words, it's only affected, it's only aware of the P waves in the medium yet. So if you look at the figure on the right, it will undergo the characteristic decay, not as strong as a sub-shear rupture, but it undergoes decay with distance away from the fault. However, if you were to march along the marked front and measure what is the particle velocity, then the particle velocity has no attenuation at all. It faithfully carries all the motion that is happening at the tip of the crack all the way up to infinity. And that's because of the steady state nature of this model. It's worth mentioning the peculiar speed between the shear wave speed and the P wave speed at precisely square root of 2 times the shear wave speed. Something very dramatic happens. You are super shear because you're faster than the shear wave speed, but the mark fronts absolutely disappear. And I don't have time to give you there's a simple geometrical explanation for this, but I will skip that or for later. It's worth noting that it was first noticed by Eshelby in 49 when he was constructing solutions for a moving dislocation. We can start refining this model. We come to another class of models called cohesive zone models, where the stresses at the tip of the crack are finite, so a bit more realistic. And I'm going to show you how the stress field looks like. I showed you earlier the particle velocity field. And not surprisingly, you will see that a large amount of stresses are carried from the crack tip further into the medium by the shock fronts. Outside, where the dilatational field is dominant, the stress field undergoes the expected decay. And this was actually my first foray into super shear rupture. I was curious, I wanted to teach myself theoretical fracture. I'd never taken a class on it, so I decided to work on this. And that was a time when I had hair. And anyway, those were very simple steady state models, if you like. They're not simple, but anyway, they're simplistic description. You can go to a more elaborate model, a spontaneous rupture model, where a rupture is born at the center of this image where the two arrows are. And one end of the rupture propagates to the left, the other end of the rupture propagates to the right. We'll focus just on the image on the right. You will see the shock fronts as expected. You will see the dilatational field, which is the field outside the shock fronts. But curiously, you also see a second strong intense motion behind the main super shear rupture front. This is what we call a trailing sub-Rayleigh rupture. And in some cases, it is actually the remnant of a transition. We'll again see about this a bit later. But the other thing that's verified here is that at the super shear rupture tip, the particle velocity field is dominantly parallel to the fault. At the trailing Rayleigh, the particle velocity field is dominantly normal to the fault. We can extend this to 3D, again using the same cohesive zone like model. And we can start to intuit what to expect from a 3D super shear rupture. So you see a half plane shown in pink, that's the fault. The light pink represents the part of the fault that's sliding and it's locked below a certain depth. The rupture front is that's straight line. And simply extending the concepts from 2D, now each point along the rupture front is going to generate a shear mark cone. And there's a strong shear mark cone that will emerge at the interface between the locked and the sliding part. And the envelope of all these mark cones will result in these shear mark fronts. And to be honest, that's what Eric and I and Jim at that time were expecting. And long story short, we started seeing features that we didn't expect, and we were troubled by it. But luckily, Jim and Renata were visiting Paris, and they happened to see Raoul, who, without even looking at the results, said you should also expect Rayleigh mark fronts. Which is not something you see in 2D. So after getting that instruction, we try to intuit why you should get Rayleigh mark fronts. So the easiest way to imagine is as a rupture tip propagates along the fault, it causes the medium to bulge on one side of the fault and dimple on the other side of the fault. And this temporarily, if you like, violates the traction-free boundary condition. So Rayleigh waves emerge to ensure that the traction-free boundary condition is satisfied. And if the rupture is super shear, it's super Rayleigh by definition, and hence you'll have Rayleigh mark fronts. And we verified this very carefully by looking at different measures and showed that, yes, these Rayleigh mark fronts are actually there. And you'll see them highlighted by the dotted white line. And just to show that these are not shear mark fronts, I have also plotted the expected shear mark front in the solid white line. And you'll see that you can see that these are truly Rayleigh mark fronts. So how does a particle velocity field now look like? I'm going to focus on the quarter plane on the surface of the Earth. That's highlighted by that yellow box in the figure on the right. The figure on the left shows the fault normal velocity for a sub-Rayleigh rupture because it's the dominant one. All the results were non-dimensionalized, but there are some numbers at the bottom and the left. And you'll see that, as expected, most of the intense motion happens at the tip of the rupture. However, when you have super shear with two shock fronts now, you will see that the shock fronts carry this information from the rupture tip to quite a distance away from the fault. At this scale, we are talking about of the order of 50 kilometers. You have two shock fronts, thing to keep in mind, shear and Rayleigh, carrying different types of motion to quite a large distance away from the fault. We so far only talked about sub or super shear, and a natural question to now ask is, how does a rupture actually go from sub shear to super shear, keeping in mind that it's not trivial for it because there's an energy barrier in between. So I will illustrate the mechanism that Burridge proposed and Andrews numerically verified. It's famously called the mother-daughter transition mechanism, or Burridge-Andrews mechanism. And here's just a reminder why it's important. I'm plotting the normalized energy flux into the crack tip. So how absorbent, if you like, is the crack tip for the energy flux coming from the medium. And as a rupture accelerates to the Rayleigh wave speed, it becomes easier and easier for it to absorb and propagate and accelerate to the limiting speed. And where I have the dashed red line, in fact, if you plot the solutions, this normalized energy flux is negative. And that's what Kostrov alluded, that the crack becomes a source of energy rather than an energy sink. And that's not mechanically admissible. And then you have the super shear regime. So the mother-daughter transition mechanism works the following way. You can look at the image on the left. What's shown is the state of stress on the fault. From approximately -1 to +1, at approximately -1 and +1, you have the rupture tips slightly behind. And ahead of the rupture tips, you will see two peaks emerging. These peaks are traveling exactly at the S wave speed, so they're precisely at 1 because we have non-dimensionalized time accordingly. And if you zoom into the peak, as shown in the figure to the right, and you say that, suppose I have some kind of a failure threshold for this interface, and a certain section of the peak violates or overcomes this failure threshold that's marked by the, let's say, the dashed S line, then that part of the fault starts sliding. And since it's born at the S wave speed, it's by definition super shear. That crack will merge with the main crack, and you will eventually get a super shear transition. The caveat emptor is in 2D, Liu et al. And in 3D, Bizzari and Das showed that continuous transition is possible under certain conditions, condition being that the shear traction on the fault is very, very close to failure threshold. So while I've so far focused on what's happening on the fault during transition, we started working recently and started to focus on what happens off the fault during super shear transition. And what is clear in these three figures is the following. In the At the middle of each of the figure, we have the fault. And what's shown in color in the top figure in dashed lines and in color again in the bottom figure is damage or failure, or the region around the fault where stresses violate some sort of a failure criterion. And what is evident, regardless of what mechanism you use, plasticity, discrete damage, or continuum damage, is that at super shear transition, you have very little to no damage. And that's actually due to Lorentz contraction of the crack tip as it races up to the limiting speed, the Rayleigh wave speed. You can read more about it in the reference there. So there is an additional signature of super shear transition, at least from theoretical and numerical arguments. So I'll now quickly transition to what I did and what we know about super shear experiments, super shear ruptures from experiments. It's important to acknowledge Francis Wu's 72 experiments, stick slip experiments in Columbia resin, where he had a pre-cut fault in the figure on the left, a series of strain gauges close to the fault. And by looking at the arrival of pulses on the strain gauges, he could essentially get a rupture speed. And shown on the figure on the right is the distance time curve, and he did actually get a super shear rupture. But he himself acknowledges that as Vietman's 69 theory disallowed super shear, he didn't make a big stink about it, as I would have if I was in his position, the first person to see super shear, and it was forgotten. And anyway, that's my guess. It took a long while, and Lambros and Aris did bimaterial shear impact experiments where they had two plates bonded with a starter crack denoted by that arrow and the letter A. And this was impacted by a projectile from a gas gun. And you can imagine if things are fixed at the bottom, you have some sort of a shear motion happening at the interface between the two materials. And using CGS, coherent gradient sensing technique, they produced the very first image of super shear rupture. So there's a clear rupture running along the interface. And you can see a dense concentration of fringes in the image on the right that have a linear-ish feature, and that is the shock front. This was metal and a brittle polymer. With Samudrala and Demir Kocher, Aris revisited these experiments, now taking brittle materials and again doing a shear impact experiment. And this time they used photoelasticity, as homolite is photoelastic, and produced these beautiful images of super shear rupture, manifesting those nice linear fronts called the shock fronts. And if I know my history right, this paper probably triggered Michel Bouchon's interest in super shear ruptures, and I'll come to that in a bit. But these experiments were good from an experimental solid mechanician's point of view, but not at all convincing for earthquake folks because there's nothing impacting, the plates interfaces are bonded, et cetera, et cetera. So with a student, Kaiwan Zia, Aris revisited these experiments, and Hiro Kanamori, and this time did experiments where they produce spontaneous shear ruptures, so something that nucleates spontaneously and then propagates along the interface, unlike an impact. And the interface was frictional. And they showed that super shear ruptures are possible using photoelastic techniques again. The figure on the left, you can see an inclined line. That's the fault interface. And the contours show the changes in the maximum amplitude of the maximum shear stress in the medium. The rupture tip is highlighted to the left. The rupture is subshear. And the circular like front you see there, that's actually the shear wave front. In the figure on the right, you'll see that the rupture tip has gone past the circular front, and manifests the shock fronts, those linear fronts, and that's a super shear rupture. So that's, if you like, the first image of a super shear rupture along a frictional interface. This laboratory setup, these were the good old days. The lab's changed quite a bit now. I spent 4 good years of my postdoc in the sub-basement there with Mike Mello on the left, running the experiments, and me on the right on that blackboard, sketching and plotting and coming up with things. And one of the things we did in that in that lab was we verified the ground motion signatures of super shear earthquake, this dominance of fault parallel and fault normal motion, the trailing Rayleigh front, etc. And it's best visualized here. The 2 figures on the right show particle velocity fields akin to a velocimeter as a super shear rupture passed by. The figure on the left is for a sub-Rayleigh rupture, where the fault normal component in green is bigger than the fault parallel component, whereas for a super shear rupture on the right, the fault parallel component in red is bigger than the fault normal component, followed by a big swing in the fault normal component, which is the trailing Rayleigh rupture. We also did scaled reproduction of a natural earthquake, and using carefully derived scaling arguments, we were actually able to reproduce the ground motions recorded along an accelerometer during the 2002 Denali, Alaska earthquake. I'll revisit this a bit later, but it was one of the most amazing things I'd seen, because the lab experiments were done on 2 plates of brittle plastic polymer, shown in the yellow, in the blue line, and the red curves is nature with all the madness that it throws at us. We also managed to capture this very rare beast, the mother-daughter transition, shown in the sequence of images from left to right. At left, the rupture is approaching the Rayleigh wave speed, and in the middle, a daughter crack is actually born, and to the right, the daughter and the mother have merged, and you have a super shear rupture. I call this a rare phenomena to capture because this happens on a very short time and length scale. And of the 250 odd experiments Mike and I ran, this was the only one where we actually managed to catch it. But skeptics are skeptics. It was brittle plastic after all. So people still didn't believe in super shear rupture. And there came Alex Shubnel and Francois Passeleg, his PhD student at that time, who did experiments on rocks, if you like, in a triaxial setup just downstairs here at ENS. The fault is pre-cut into a cylindrical specimen and then put back together and subject to massive loads that are comparable to crustal loads. And using acoustic transducers, they clearly showed the emergence of a super shear rupture in this experiment. And to be doubly sure, they also verified this along with me by comparing the recorded motion with a theoretical model of a super shear rupture. And that's shown by the black lines on the figure on the right. And Since they agree, there's absolutely no doubt that the lab experiments here also went super shear. What was also shown by Francois at that time were two key observations. One is that super shear rupture is obviously possible under crustal conditions and in rocks. Transition to super shear requires two things: that the S ratio has to fall into a range as anticipated by Joe Andrews, Shamita Das, and Aki, etc. And you should have long enough fault length for the transition to occur. So essentially, your runway should be long enough for the rupture to accelerate from subshear to launch off into the super shear regime. I will quickly walk through now some of the observations of super shear earthquakes in nature. The first observation or inference, if you like, of a super shear earthquake was made by, actually really by Ralph Archuleta in '84 for the 1979 Imperial Valley earthquake. And I'm paraphrasing Shamita's review paper here. This was not universally accepted. And of course, the scale tipped again in the favor of super shear skeptics for 25 years, which means we might have missed quite a few super shear earthquakes. But luckily or unluckily to be precise, but luckily for the science, two twin earthquakes struck Turkey, the '99 Izmit earthquake and the Düzce earthquake. '99 was a year when RS also published the super shear observation in the lab. And Michel very clearly showed, using a station very close to the fault, that both ruptures went super shear. Here's an example from the the '99 Izmit earthquake from a station not too far away from the epicenter and the fault. And what he essentially saw, as shown in the inset figure there, is that the motion arrived before the theoretical arrival of the S wave, highlighted by the letters P and S. So the difference between P and S times was shorter than theoretically expected, which was a clear signature that things went super shear. We revisited this earthquake to say, can we find any hints of super shear transition by looking at what's happening off the fault? And as stresses are, as the region around the fault that gets stressed during the transition is very small, we made the hypothesis that early aftershocks, a few days at the most right after the earthquake that have been loaded by the rupture, should have some hints, or more specifically, the distribution of aftershocks. And what we see is that indeed, around the region where super shear transition is expected, there is a paucity in aftershocks off the fault. And this paucity in aftershock is exactly related to the images on the left, where the damage or the stressing is very narrow and confined close to the fault. After the '99 twin earthquakes, you had the 2001 Kunlun earthquake that Michel, Shamita, and many others studied. I worked on it as well, mainly to look at what explains this anomalous cracking that was serendipitously observed at the distance of several tens of kilometers away. And what we hypothesized was the shock front, the mark front carrying large stresses might have loaded and unloaded this region that might have dynamically nucleated these fractures. We revisited this earthquake again to look at what happens at transition, this time using image correlation techniques to actually visually see the damage zone. And we again see a shrinkage of the damage zone around where super shear transition occurs. Then exactly a year after, the Denali earthquake struck in Alaska, which had the cleanest record, near field record of a super shear, excuse me, earthquake, where all that was shown theoretically and experimentally was cleanly validated, that the fault parallel motion is bigger than the fault normal motion, and then the main pulse is followed by a big swing in the fault normal motion that is associated with a trailing Rayleigh rupture. We redid this experiment, and we also showed that, yes, this rupture did go super shear, and because it was scaled and done in a controlled condition in the lab, we actually imaged this earthquake, if you like. More super shear earthquakes have been found. I'm going to quickly just talk about the last one, the 2018 Palu Sulawesi earthquake that happened in, September, October 2018. And this earthquake was claimed to have gone super shear by far field techniques like back projection by Bao et al., or by other techniques by Soke et al. However, we were very lucky as my colleagues here in the lab were running high-rate GPS stations around the fault. And I'm going to focus on one station shown by the inverted triangle, the pulp station. And we simply look for the same signatures of super shear. The figure on the left shows the fault parallel motion. The figure on the right shows the fault normal motion. What's shown in dashed line is what was recorded at the GPS station. The curves look a bit sharp. That's because these were recorded at 1 Hertz, as opposed to the acceleration records at Denali that was at 250 Hertz. Regardless, the fault parallel motion is bigger than the fault normal motion. And we cross-validated that with the dynamic rupture model to say, yes, this rupture did actually go super shear. So I'll conclude by simply saying that dynamic shear ruptures, including earthquakes, can attain super shear speeds. In fact, they can indubitably attain super shear speeds, because I always come across skeptics. And it's one of the rare occasions in earth sciences where I get to use the word indubitably. A quick summary is that super shear ruptures are stable above the so-called Eshelby speed. During super shear ruptures, particle velocity is dominantly parallel to the fault. There is a clear separation of shear and dilatational fields, which manifests in the ground motion. They are usually trailed, not always, by a trailing Rayleigh pulse. And this pulse has dominantly fault normal motion. In 3D, you get 2 Mach fronts for the price of 1. And the second Mach front is the Rayleigh Mach front. One can talk a lot about this because these are associated with surface waves. They can go much further. They suffer from a different, weaker kind of attenuation than shear Mach fronts. And they carry a lot of vertical motion. And finally, at the location of transition, due to severe Lorentz-like contraction of the stress field, you should expect very little off-fault damage. I'll do the obligatory thing that I'm supposed to do during HDR. So I studied civil engineering, and then I did mechanical sciences essentially at Harvard under the supervision of James Rice and Renata Dmowska, focusing or applying solid mechanics ideas essentially to the study of earthquake sources. I was very lucky and privileged to then do my postdoctoral work between Caltech and University of Southern California under the supervision of R.S. Ozakis and Charlie Samis. I spent 4 wonderful years over there. And then I got very, very lucky again, and I got recruited as a CNRS research scientist, which started my journey here in France. I'm very proud of the fact that I was in the middle of a job interview at MIT when I got the call saying I got the job, and my proudest moment was to say no and walk out of the meeting. And I just packed my bags and came to France. I've never regretted it, and every passing day just reinforces that decision I've made. Some numbers about publications and funding. Funding is a bit tough, as you can see here, but I never give up. Those of you know me, and I just keep trying and trying. But one of the beauties of being in France and the system here is that you don't stop because of lack of funding. There are always ways by collaborating with folks like Alex over here, Jan Klinger down, that you continue your science at a slightly different pace. And not to forget all the folks who have actually driven me and helped me learn and help me pursue the vision I have. I thank you from the bottom of my heart. I have actually learned more than whatever I could ever teach you during this time. This is just a mix and match of folks I've worked with who have influenced me tremendously. As far as scientific contributions that are other than supershear ruptures go, we developed simple rules for rupture branching. This was, in fact, my main thesis work with Jim and Renata, explaining forward and backward branching in a fault network. We also developed novel algorithms to model earthquake cycles in a fault network, like in the figure on the left. And we showed that you can actually have slow and fast earthquakes spontaneously and naturally the moment you step away from a planar fault. Working with several folks over the years, partly during my postdoc with Charlie and Aris, we showed that off-fault damage dynamically interacts with an earthquake rupture. And we developed micromechanical models of the mechanical and hydraulic response of the fracture network surrounding a fault. We showed that you have high frequency radiation coming not just from the fault, but all these additional fracture networks that are activated. And with the colleagues at Los Alamos, we co-developed algorithms to spontaneously activate these off-fault fracture networks. And with Victor Cruz at UNAM, we also explained, or tried to explain is the right word, migration of tremors in the damage zone by alluding to nonlinear fluid diffusion mechanism. With RS, Hiro, and Raul here, we also showed a bizarre thing, but quite fascinating, that under certain conditions, thrust faults can actually open. And all this journey over the past 20 years, if I count it from the moment I started my PhD, has allowed me to put this grand picture together, which is to understand the intricate relationship between fault and fracture networks at these various length scales. And I've been very lucky to be funded by the European Union to pursue this. And the project just started a few weeks ago. A big, big thank you to the following folks, because while coming to France was scientifically and intellectually the right decision, it was a new country. I didn't speak the language, and more importantly, I absolutely did not understand the system. Not that I understand it any better almost 10 years down the line. And I did go through several long periods of low. But thanks to Jimedo, Alex, Claude, Nikolai, Jan, Eve, Jeff King, Joanna, Nobu, Raul, they gave me the courage and the strength to continue pursuing my science, and became my good friends over time, to which I am eternally, eternally grateful. Two people deserve particular thank you, which are Laurence Boudleau and Marion Thomas, the two women in my life, really, who have made me who I am today, who have kept this crazy ship afloat. Last but absolutely not the least, my love and respect and a big thank you to Jim and Renata, naturally my academic parents, but my American parents, I consider you my mom and dad. So thank you for everything. To Ars and Charlie, who saw things in me that I never recognized and lifted my spirit. To my sister, Dipti, whose love hasn't changed from the moment that picture was taken. It's still the same. And obviously, mom and dad, you have sacrificed a lot for me, so thank you. And to the two real queens in my life, you know who you are. Tom Tom and Nana loves you to bits. Thank you very much.
We'll wait for the jury members to be back. Maybe the jury members can turn on their camera. They are here.
Mine is on.
Okay. Alex, do you mind if I turn on the audio on my computer and you switch on that?
I turned off the audio on mine, actually. Okay, so Paul, the floor is yours. So,
Alex, I'm sorry, I misunderstood. Was that me?
Yes, in fact, you're the reviewer from furthest away, meaning you're also in the morning.
No, Rosakis is furthest away.
Yeah, but
Honest.
Rosakis is not
This is even further.
the reviewer.
Rosakis is furthest away.
So I'm happy to start.
Normally we start with reviewers. I'm really sorry, Aris.
It's fine, it's fine. I'm still drinking my coffee.
So in any case, knowing probably the least about this phenomena of all of the jury, it's appropriate for me to exhibit my ignorance on the topic. But Harsha, that was a really great presentation, and I really appreciate the clarity and the simplicity of your visuals, and I really mean that. There's so many bad presentations out there, and yours was a great example of how to give a really good presentation that everybody technically literate can understand. So thank you very much, and I appreciate everything you've done in terms of the scope and breadth of work that you've accomplished so far. I appreciate your friendship and knowing you as well, and all your colleagues at EMS and IPGP. Also, it's clear that the HDR for you is really is a necessary paper, but you've been working at the level of a professor for many years. That's obvious. So this is sort of a pro forma exercise, but just necessary exercise because it's France. So also the document, Harsha, is excellent. And I found that the thesis, just like your presentation, was remarkably clear, remarkably comprehensive, The figures were excellent. You spent a lot of time reworking the text, the document, everything, you know, as I mentioned in a note to you, Harsha. So it's excellent archive as is because it's so good. And I found it remarkably clear, remarkably comprehensive. You spent a lot of time reworking the text as a review paper for something like Reviews in Geophysics. Also, if you consider doing something like that. So I have just a few questions, and they're questions regarding things you didn't cover in the thesis, but for me, they're quite interesting. They may not be so very important in regards to the work you've done, but I find them interesting. So let me pull up my list of questions. So the first question, Harsha, is regarding dynamic triggering. And I'm wondering if, so there are different, okay, in subshear, dynamic triggering, and I found that the rupture front, ahead of the rupture front, could be important. There's been some work in this area, and I'm only familiar with a little bit of it. One would expect this to have less of a, you spent a lot of time reworking the text, an impact that you, Harsha, I think should presumably. I'm just wondering if you have any thoughts on this. Is there any evidence for this?
Sorry, Paul, some of your audio got gobbled. So if I understand correctly, well, why don't you rephrase it, ask me that question, please?
Because they have less of an impact on this. Is there any evidence for this? Okay. Is the audio better now?
Yes.
Okay. So Harsha, sorry about, I think my connection's quite poor. So apologies to you and everybody else. So here's the question. It seems that dynamic triggering in front of the rupture could be important. I know there's been some work in this area, and I'm familiar with some, but not all of it. In contrast, super shear rupture may have less impact, presumably. And this is along the rupture path, along the fault itself. I'm wondering if you have any thoughts on this, and if you have, in terms of simulation or observation, have any evidence for this idea?
My short answer is no. I mean, your intuition's right. It's a bit hard to imagine, if I understand you correctly, triggering ahead of the rupture front during the shear rupture propagation. Because you have what's ahead of the front is essentially the Doppler affected P wave field, and it's traditionally quite weak, not strong enough to trigger anything. From natural earthquake observational perspective. Numerically, I never tried it, but I'm certain one could delicately rig the state of traction and friction on the fault, that there is a possibility of triggering of some kind of a thing. Not during a planar fault rupture, but when you have a non-planar fault, then you have changes in shear and tractions because of the gravitational waves, and that might possibly trigger. So that's my guess, to be very honest.
So it just seems like in subshear, since you have both wave fronts propagating in front of the rupture, that you might have different, if triggering actually takes place, and in my mind it should, there would be different characteristics than you would have in super shear. And so that's really the heart of it.
Yeah, it's shear rupture, subshear. The biggest peak is in the shear traction that is carried by the S wave. And that is big enough to, under the right conditions, to violate some frictional resistance, and you have a triggering ahead. Having said that, there are, I should also say that there are other ways in which you could trigger things ahead. That you had, let's say, a very favorably oriented secondary strand that had favorably in the sense of stress, and if it was frictionally also under favorable conditions, then it's possible.
Right. So that really makes sense. So I think fundamentally the question is getting at the question of can super shear influence rupture size in contrast to sub shear, and again it's something you may have looked at in detail or not, but I just would like your thoughts on that question.
Well, so that's a bit of a tough one to answer, but let me make it. Now, if you go by by what I've shown, okay, on how things super shear. In all fairness, that's one of the mechanisms to transition to super shear. But let's say that mechanism is operational. Then that notion of transition length comes to play. So you anyway need a minimum length of a rupture for it to go super shear. So from that aspect, you could argue that super shear ruptures are bigger than sub-shear ruptures. That's a bit of a hand-waving argument, but that's one answer. Having said that, it's also worthwhile keeping in mind that you can get super shear ruptures under controlled conditions, but nevertheless, in lab scale experiments, be it on homolyte under orders of tens of MPa of normal and shear stresses, or be it in rocks here with stresses of the order of several tens to several hundreds of megapascal. And there we are talking about faults of the order of tens of centimeters. So the picture I have in mind, to be very honest, is that, and there's no observational evidence, this is pure gut feeling, is that if you imagine faults having very heterogeneous strength distribution, then I expect lots of small super shear transitions to occur all the time during an earthquake rupture. And it's just that we can't observe them with accelerometers or any other technique. They're too tiny and they very quickly attenuate away from the fault. There is a big open question, which is if what I say is right, then how do all of these guys collectively then become a large super shear rupture like we have observed? The 6 or 7 that I've listed are magnitude 7 plus earthquakes, except the Imperial Valley. So that's my attempt at the size of a super shear rupture vis-a-vis subrailial rupture. So you can have super shear at small scales on one hand. On the other hand, you need a minimum length for a rupture to go super shear, so it has to have a certain size anyway. So as always, I have further modeled the question than actually answering it.
Can I say something?
Please do, Shimita.
Because, you know, Imperial Valley was supposed to have had super shear in the first few kilometers. So there was no minimum length for that one.
Right, and yes, that's why I mentioned before that assuming transition mechanism I said earlier was right. In fairness, Palu 2018 is supposed to have gone super shear right out of the barn. So there are exceptions, of course. And short answer is we don't know. We don't know all the details.
excuse me, I was muted. It's fascinating because, I mean, you pointed out something I was wondering about, Harsha, that you might have frictional patches, friction. Some of them are super shear, some of them are sub shear simultaneously, as I think you were alluding to, and there must be this interplay between them, and then somehow those coalesce into a primary super shear event. Am I imagining that properly?
This is one possibility I think as well. There is a nice paper by Dunham in 2003 where he showed that subshear rupture, as it encounters a stress barrier, first navigates its way around it because it finds it very hard to push through this barrier. But there is a local buildup of energy. And this local buildup of energy is sufficient that once this barrier pops, it pops at super shear speed and it catches up with the rest of the rupture. And this is, one of those asperities that I was imagining. So it's possible. We have to devise very, very clever observational techniques to see it. And I'm not the guy.
Well, in terms of simulation, though, you are the guy, and that seems like it could be fascinating to attempt to do something like that.
Yes.
I'm thinking it's probably in the back of your mind in any case.
It's an open question that has been on my mind ever since I started working on this, which is how do small scale super shear ruptures blow up into large scale ruptures in a heterogeneous stress or resistance field, if you like. It will be pursued. Human resources.
Right, understood. Now you've got some funds to pursue it, so hopefully we'll see something like that in the not too distant future. Sort of along the same lines, you might expect that super shear wavefront might be a powerful trigger of adjacent faults. Certainly you're creating off-fault damage, but you're doing that as well for subshear. But the Mach front, just like in the atmosphere, could be very large in amplitude. Of course, you have much more dissipative material in the elastic medium. But do you know if there's any evidence for enhanced dynamic earthquake triggering away from the fault during super shear in contrast to subshear?
Yes, the gentleman to your left in my screen, of course, Michel, has looked at this for the Izmit earthquake, where you see a broader distribution of aftershocks in terms of distance away from the fault along sections where the rupture went super shear. And you alluded to a very good point that I think a lot of people probably don't think too much about, is that the analogy between supersonic and super shear stops at the fact that there are Mach fronts. That's about it. Because they are strong shocks in fluids. They involve density changes, etc. And they're very powerful. So when we say the word weak shock in solids, we are talking about a weak shock. There are barely any discontinuities that are carried by these shock fronts. So the shock fronts themselves, it's hard to imagine the shock front destroying buildings and things of that nature. It is easier to imagine shock fronts carrying large ground motion to distances much further away and raising stresses on nearby off-fault structures, secondary faults, and things like that, much more than what a classical subshear earthquake would do.
Yeah, so so that's interesting, and it makes it makes sense. It's logical. Let's see. I'm just looking at my list of questions. I don't want to go through all of them because I don't want to commandeer all the time. Yeah, in fact, my last question that I jumped down to was this issue of simultaneous subshear and supershear due to the frictional characteristics of the fault. So we've already been through that. So I think unless you have further comments regarding that point or the triggering question precede out in front of the fault or away from the fault, I think I would turn the questioning over to my colleagues.
Well, you raised a very interesting point, which actually is in line with what's been bugging me at the back of my mind. I need to think a little bit harder before and do some back of the envelope calculations before I say something silly. So I would actually like to catch up with you, Paul, offline, and we can continue this discussion if you don't mind.
Sure, of course. That sounds great. Well, thank you so much, Harsha. Again, congratulations on the terrific thesis, HDR thesis, and on your presentation. Really appreciate it. And Alex, I'll turn the floor back over to you. Thanks, Harsha.
One second, Alex. I should have said this first. Thank you very, very much for your kind comments, Paul. I'll catch up with you after.
Excellent.
Okay.
Thanks, Harsha.
Okay, thank you very much, Paul. So the next it will be Michel Bouchon, who is also a reviewer of your manuscript.
Thank you, Alex. Yes, it's I can only repeat Paul's comments on your manuscript. It's really and it would be great if you could if it could be available to a broader audience than just your committee. Okay, it's really so well done. Congratulations, and for your work as well. Now so I just go to the questions, and I'm going to ask you basically two questions, and they are related to some of the questions I've been asking myself in the past, okay, and they are related to observations.
Okay.
And one of them is what we call the damage zone or the fault zone, and in terms of width away from the rupture itself. And we know that for some well-studied earthquakes, that there is typically what we call a fault zone, which is typically at the scale of 100 meters or of that order, and in which there's reduced shear wave velocity, strongly reduced, maybe by as much as 50% easily, because of cracks and damage. This we know does exist for sub-Rayleigh for some sub-Rayleigh earthquakes. Now, what should we expect for supershear rupture compared to that?
Okay, very good question. My short answer is not that dramatically different once the rupture has matured to super shear speed. By mature, I mean if it has grown into a reasonable length. I'll make the argument from the following perspective. If you imagine a pulse-like rupture, because you're talking about observations, I talked only about cracks. If you imagine a pulse-like rupture running along a fault and then transitioning to super shear, what I showed earlier holds true as well, which is when it's subshear, singularity at the tip of the crack is the strongest, let's put it that way. It's a square root singularity. When it goes to super shear, the singularity is a bit weaker. And depending on the speed, it's a number between 0 and 0.5, which means that the stresses impinged by this rupture on the surrounding medium is a little bit weaker, which in turn will activate less of these off-fault fractures, etc. And possibly a hint might lie in how much reduction in wave speed in the fall zone we might have because of this less activation of fractures. It's something that we will address much more carefully as part of my ERC project, because in it we have tools to model damage and reduction in wave speeds, etc. And we have some hints about it, but I'd rather do this carefully in detail and get to that.
So one aspect of your answer, you don't expect a fault zone of a finite width like it is observed for subrelay ruptures?
No, I do expect, I mean, I expect a damage zone. I suspect it's going to be a bit, how to put it, its width might not be that dramatically different from a subshear rupture, but the density of fractures, the size of fractures that got activated within this damage zone might be different, because the stresses, stress field around the super shear rupture is slightly weaker because the singularity is weaker. And hence, there might be a hint in the reduction in the wave speed within it. I don't expect the width to change that, that dramatically. Having said that, we need to look at it much more carefully, and we have the tools to do it. And in fact, there's even a student who will actually come and work on it, but he's stuck in Mexico City right now. He'll be coming here soon.
Okay, thank you. Okay, another question concerns the sleep partitioning.
Okay.
Because we know that what works for strike sleep is different from deep sleep. Mm-hmm. And we also know that faults are more complicated, okay, than having just one mode of rupture. So I imagine it's a very complex problem in terms of in theory, but how do you expect a motion which when it is subrelay is not pure strike sleep, simply contains some deep sleep component, then it transition, or at least a strike sleep component transition to super shear? What happens to the deep sleep?
Okay, but you're still.
RSS.
I'm amused. Yeah, I like this question.
Well, I'll give you a geometrical argument. Okay, here's my take at it. So I'm still thinking about a vertical fault for the sake of this discussion. and rupture nucleates somewhere at depth. And for the sake of argument, and like you said, it can have mode 2 or mode 3 component. It will have a complex mixed mode rupture, no problem. What we know for sure, this is fundamental, is that the mode 2 component can go super shear, and the mode 3 component is limited by the shear wave speed. And Shamita's nodding her head because I should have started that way. Shamita with Andrea Bizzari explored this numerically in 2012. But here's what you should expect. Imagine you started with a nice circular rupture front. The motion parallel to my mouth is mode 2 and parallel to my nose is mode 3. So both of these ruptures, imagine they accelerate up to the Rayleigh wave speed. Okay, they have mixed mode nature. Nothing's limiting the speeds up to this, limiting the ruptures up to this speed, so they can remain circular. The mode 3 component can go beyond the Rayleigh wave speed up to the shear wave speed, so your circular rupture starts changing shape. And if the conditions are right, the rupture to the right might accelerate or not.
So you mean the fold can slip, let's say horizontally, and a few seconds later, slip upward?
No, I'm just resolving the general sense of slip into mode 3 and mode 2 components.
I understand, but is it? We know that a fault has a topography determined by the way it slips. Okay, the direction of slip.
Mm-hmm.
So how could the fault slip horizontally and a few seconds later the same location of the fault would slip upward? You see?
No,
slip is in one direction only. Slip is everywhere in one direction. It's the rupture that is moving in different directions. The slip is only in one direction, parallel to the local tectonic stress. It's just the rupture that's propagating in different places. Slip is the same. Direction is constant. Or very, very small changes maybe, but mainly.
Yeah.
Can the same fault host both the strike-slip component, which
in theory, small amounts, yes.
Yeah. Because what is, I'm not convinced, Shamita. And indeed, in Kunlun, okay, what is observed is partitioning. It's not the same fault which is playing strike-slip and.
No, I think we are just confusing terminologies here. I think we are all saying the same thing in our own.
One is slip and one is rupture. And it's not the slip direction is more or less constant. There can be small changes around obstacles or something locally. But the main slip direction is the same, but it's the rupture is propagating in mode 2 or mode 3, the rupture front.
And
so if you have a circle, it's going.
Okay, if you take the observations of Kunlun,
mm-hmm.
In Kunlun, there are two faults. There is the pure strike-slip, the pure horizontal motion of the main fault,
mm-hmm.
which is on average about 5 meters.
Yeah.
And a few kilometers away, parallel to it, there's a secondary fault, which has pure deep slip motion,
mm-hmm.
much smaller, but reaching about 50 centimeters. And this is true over more than 50 kilometer lengths, where the super shear occurs.
No one's, I'm not at all disputing that. thing to keep in mind is when, by the time the rupture reached the part where the Kunlun fault, let's say, has two strands, the dip slip and the strike slip fault, the rupture is quite mature. And here we are not talking about a circular rupture or an elliptical rupture front with mixed mode type fracture. Here we are talking, at this stage, the rupture is practically a vertical front, approximately, that is sweeping along the main strike slip fault. And the motion is pure strike slip there. And stress perturbation induced by this rupture, either at depth or dynamically induced, triggers the motion on the dip slip fault. So I'm not saying, I mean, we are talking about different parts of the rupture, if you like. What I was saying was at the very, very initiation of the rupture, you have, let's argue this way. As Shamita said, slip will point in the direction of traction. Traction has components along the dip slip side and along the strike slip side. They are not exact, they're not equal. Obviously, one is dominant compared to the other. On a strike slip fault, it's dominantly the horizontal component of traction that is dominant. And associated with that, there are modes of rupture. So a mode 2 or a mode 3 rupture, and they have limiting speeds. And that's about it. And anyway, all this becomes moot as soon as the rupture I talked about, let's say, saturates the depth.
But you see, I understand your explanation and I understand Shamita's, but you make this, there is exactly the same observation during the earthquake. The strike slip fault, the main fault, the North Anatolian fault in that case, has no vertical offset at all when it's really well marked. Okay? No vertical offset. The vertical offset is a few kilometers away at the bottom of the hills, and it's parallel to it. Basically, it's like we have two fault systems, at least near the surface. At depth, they may be the same, I don't know. But you see partitioning, and you see in Kunlun, it's the first time the tectonicians saw slip partitioning during the same event.
Michelle, I just have one question.
I don't.
How do we know that second fault happened at the same time as the first fault? It could have happened, a few minutes later or next day when the stress, another component of stress builds up. We don't know that one happened at the same time.
You're right. But it happened within a few days or a week or so.
But that can happen due to stress redistribution, some kind of.
Well, I think you may be right. But if you look at maps of the Kunlun fault or maps of the North Anatolian fault before the rupture, before the big rupture of these two large earthquakes, you see that the position where the fault is traced by the geologist is not where the rupture, where the supershear rupture occurred. It's not, because the geologist put the fault where the deep slip motion is, because it's where the topography is built. The strike slip motion is pure strike slip in both cases, and it disappears a few years later because it creates no topography. So I think it's more important than what we think. Okay, it seems to be a double system. Well, anyway, I think that's
Maybe
worth thinking about this.
I just want to. I mean, in terms of friction, it's hard to have both on the same fault because because of Andersonian faulting theory. No, I mean you will not be able to activate a strike slip fault like in deep sleep. So you have, in terms even in a static manner, you have to have you will even trigger a new fault. They can probably propagate the two together, but Andersonian faulting kind of prevents the activation of a purely vertical fault in deep sleep. Or maybe I'm completely, I don't know.
No, it's not a purely vertical fault. Sorry, it's the deep sleep function takes place on a secondary fault,
Yeah.
which is a typical deep sleep fault.
Mhm.
Anyway, I think this is worth, because of the audience and the jury here. I mean, I think that's worth thinking about this because there are observations of this phenomenon.
I'd like to make one note. Is it's been a long while since I wrote that paper. It's coming back to my mind. Is when we looked at the Kunlun earthquake back in 2007 with Jim, Renata, Jan, and Jeff. I also calculated the Coulomb stress change carried associated with the super shear rupture.
It's opening cracks, yeah.
Yes, it's opening cracks for sure. But what's under certain conditions, the stress perturbation carried along the mark fronts under plane strain conditions, mind you, is such that it can also invoke dip slip motion. And I did this for the dynamic stress field, okay? So I wouldn't take my observation far enough to say this would trigger a big rupture along a large secondary strand, but suffice to say that the stress perturbations under certain conditions carried by the mark front are, from an Andersonian faulting point of view, or more precisely, or more Coulomb, are conducive to initiate dip slip motion, normal law thrust, on off-fault structures.
Okay, Harsha. I just want to point to one thing, okay, is that you take that Kunlun fault. That Kunlun fault, which is super shear because it's pure strike slip in the segment, at least we and Shamita also worked, okay? The deep sleep associated with that fault has built mountains there. Okay, there's a mountain range. Just at the bottom of that mountain range is that deep sleep component,
Yes,
which ruptured during the earthquake. Okay, anyway, I just wanted to bring this to your future attention. Okay.
yes.
I did want to mention that at the Kunlun earthquake, not a single aftershock had strike slip motion. You remember that?
Yes, yes.
Yeah, that means there is other kinds of stresses sitting along there, giving you other kinds of faulting. Yeah.
But the Kunlun, just to end up, the Kunlun fault runs at the bottom of that mountain range. So I think that's not an easy question theoretically to answer. I understand. Okay, thank you very much. Thank you, Alex, and congratulations, Harsha, for beautiful work. Really beautiful.
Thank you, Michelle, for your kind words and encouragement all the time.
Thank you very, very much, Michel. So the next, the third reviewer of your manuscript is our colleague from Sorbonne Université, Jimedo Kondo. So Jimedo, un plaisir de t'écouter.
Okay, thank you very much, Alex. Harsha, if you remember, we first met from scientific side at summer school at Carrières. It was a school where we tried to meet people from physics and mechanics. And at this moment, I was very impressed by what you showed during this summer school. And it was very nice to discover at this moment your research topic in detail. And I was very happy when you asked me to be there today. So congratulations for what you present today, but also for the document that you present. Generally, for an habilitation for research, there are something which are generally asked. First, the candidate might be scientifically identified. That means that you have a clear identity from the scientific side. And for me, it's clear that from your what you develop during your career and what you present today, that there is no doubt that you are an excellent scientific, and that you can play with people from different sides, from solid mechanics, which is the domain in which I play, geophysics and physics. And I think that this is a very important point that I would like to underline. Okay. I am also, it is important to note that you make the supervision of several students, and now you have several students with Alex and the other one, and this is something which is asked for the habilitation for research, and this is a good point also. I have a few questions. I will say from solid mechanics point of view, but the first question is that I understand that the mechanisms which are under Supérieure FKX combine friction and fracture propagation. Okay, and my question is, what do you think about the viewpoint of J. Vandenberg, who thinks that friction and fracture is friction?
I love that question too.
That's a short question, as always they are, shorter they are, with a very, very long answer. I mean, if I understand Jay's perspective correctly, so let's go through this. You have two blocks with an interface, a frictional interface, subject to a normal load and being pushed from one side, so subject to a shear load as well. That sets up shear and normal traction along the frictional interface. And then he, using essentially two different techniques, imaged the rupture. He looked at the interface and he looked at the strain field carried by a dynamic rupture running along the interface. And by using LEF, linear elastic fracture mechanics solution, he showed that the strain gauge data is best explained by a shear rupture propagating along the interface. And honestly, this is my understanding, and I suspect that's what made him claim that friction is fracture. For me, I mean, I really don't see the point in making all these types of distinctions. Because, look, let's be honest, friction is an approximation we use to describe force. It's easier to treat it mathematically and numerically. If you go at the level of, if you had the capability to zoom into a fault interface, or for that matter, any interface that has been under contact for a long while, there are hundreds of different mechanisms that are probably coming into play that eventually break the bond between these two interfaces at whatever length scale you're talking about. And then all this is globally lumped into a friction load that describes the weakening of this interface as a function of subjected loads and kinematic motions, etc. So I don't have anything big or controversial or contrarian perspective here, because I don't. I mean, for my view of ruptures are that you. Compared to our classical view of fracture, let me put it that way, okay, where you are rupturing a virgin material, creating fresh new surfaces. All we are doing is reactivating motion along an interface, and this motion is not in a rigid body sense, it's in a continuum elastic, continuum solid. So the motion is heterogeneous. It has motion and it moves, what we call a rupture, and we have slip velocity, etc., etc. That's really the picture I have in mind.
Okay, I think that I share your view on this point, because if I try to analyze for...
Sorry, sorry, Jim, I muted my speaker. Can you...
I said that I think that I share your view. If I analyze from energy point of view, it seems to me that when you have friction, the nature of the dissipated energy is not completely what we obtain in fracture. My second...
May I make a point there?
Yes.
Hi. I wanted to say that I agree with you that there are differences here, and even from the mechanics point of view, fracture means breakage of bonds with a certain strength, and there is an critical energy release rate, and in addition, fracture toughness, which is one value. When you have friction, the resistance to sliding depends on the normal stresses. So by definition, it's not a material property. So basically, although friction may have some fracture-like properties or appearances, it really, the boundary condition in front of the rupture that is propagating is fundamentally different, because the resistance itself depends on the boundary condition or on the stress state that you impose. So there is no one fracture toughness.
I completely agree with you, Ares.
In that sense, yes. I think what Harsha also said is exactly correct. That so it's misleading to actually call a frictional sliding fracture.
I'd like to just add a couple of notes. Chibedo, you made a good point that I actually have debates about this, but I completely forgot, which is, and as Aris pointed out, is if you think about a frictional rupture versus a classical fracture from a purely energetic perspective, as you said, let's stick to linear elastic fracture for the time being. All the dissipation in fracture, all the energy that is lost is happening at the tip or at the most in a cohesive zone. In frictional ruptures, Okay, if you have a crack-like rupture, let's say, there is a continuous dissipation of energy going on, depending on, of course, what the frictional law is. But for all practical purposes, you are continuously dissipating energy everywhere where the rupture is occurring. That's a big difference to keep in mind. So LEFM, even I use some of those tools, but they have limits. I can't push them too far. The second point is I haven't looked at the list of people in this, but I'm pretty certain I'm going to get quite a few emails after this. So thank you, Jivedo, for the question.
Okay, thank you. My second question is something that you discussed before with Michel about I have exactly the same question about the role of damage around the fault. And it is not clear for me why you expect that this will not have an effect, because for me, you will have a competition between elastic energy, dissipated energy, and something which will be dissipated also in the damage zone. And lastly, the kinetic energy, since you are dealing with fracture mechanics. So what are the points for which from which you can expect that this will not have an important effect? And because you discussed this with Michel, my second part, the second part of the question is, how can you incorporate damage in your analysis now?
Okay. So regarding essentially role of damage and super shear, in fact, with Kurama Kubo and colleagues from Los Alamos, mainly Esteban Ruggier, we have actually shown that under certain conditions, off-fall damage suppresses super shear transition.
Okay.
It's not a universal thing I can claim that damage will always suppress super shear transition. As you said, it's a very delicate energy balance between what's available in the medium, what energy flux is making its way to the tip of the rupture, and how much of it is eaten by the off-fall fractures along the way. The second thing to keep in mind here is that I'm talking exclusively about fall zones, where this damage is there in place. So a lot of off-fall damage I'm talking about is really reactivation of pre-existing fractures, not creation of fresh new fracture surfaces. And if and this is just my intuition, I haven't worked out a clean way to sort this out, is if you think about the evolution of a fault itself, the growth of a fault to its mature, relatively mature structure it is today at anywhere we look at, then you can imagine that this fault has undergone hundreds or thousands of rupture. Each rupture episode activating fractures or maybe creating a few fresh ones as well along the way. And if you just extend that argument, the damage zone should become wider and wider, which means the rupture should become slower and slower. But if the rupture becomes slower, then the stresses put around the rupture is not that strong enough as well. So the activation of fractures happens in a narrower region. So there's a balance that happens between the width of the damage zone that is set and a rupture that is posted along the fall. This is right now just a hypothesis I have on my end. So that's a long answer.
Okay.
regarding your second part about how to incorporate this in analysis, so if you mean looking at it from a theoretical perspective, I don't have any tools at my disposal to do this. But numerically, we have two different approaches, and we have actually looked at this a bit, either using homogenization schemes to account for fracture damage, or by explicitly modeling every single fracture that could be accumulated. And in both these computations, what we see is that, again, under certain conditions, what would have gone super shear if there was no damage goes sub shear if there is damage. But under other conditions, it just happily goes super shear.
Okay. I have thought that this has some link with maybe the cohesive zone model that you developed. I was impressed by that, but I have a question. In the cohesive zone model, you need to determine characteristic length or something like that. In situ condition, how do you expect to determine this characteristic length?
So for starters, in all honesty, if you dive deep into Broberg's book, all the solutions are there. So I didn't really develop. Regarding the cohesive zone size, what's denoted as R naught typically in our business, different meaning these days, but R naught. What Jim with Charlie Samus and Parsons explored this in 2005. What they tried to do was they essentially, we have some decent idea about fracture energy of earthquakes. And using a cohesive zone model, they gave a proposal on how to compute the cohesive zone size from the fracture energy. And you have to make some assumptions about the strength of the fault, etc. But regardless. And what they found was that this number is of the order of several tens to at the most a few hundred meters. So that's nature's size of cohesive zone size, if you like.
Okay. I have made an observation about the fact that in your document, we don't have any information about on the computational point of view. Maybe if you can comment what are the needs from computational point of view to obtain your result. And the very last question is about the role of fluid pressure in all the events that you present. Is the fluid pressure, in situ fluid pressure, play a role?
So I'll start with the last one first. Fluids play a huge role. I should have prefaced my talk that my entire discussion is happening in a dry medium. Fluids come to play in many different ways. Alex is a much better expert than me. Fluids come to play, for example, in terms of what happens to the frictional resistance at the interface. Fluids come to play in terms of poroelastic effects in the surrounding medium. Fluids come to play in terms of not in the context of what I'm talking about, but from dehydration mechanisms, etc. They all and they come to play during dynamic changes in hydraulic properties of the off-fault damaged medium. And it's in the plans to explore this. bringing in poroelastic effects on role of fluids, as you know very well, makes this super shear story even more fun, if you like, because now we have 3, 4, 5 Mach fronts, depending on which style of, well, let me stop at that. Regarding computation, yes, I've masked the computational effort that goes into this work, mainly because we in earth sciences, you know, you don't want to spend too much time writing about algorithms and things like that. No one's interested in it. So when we write papers, we just get straight to the answer. But there is a humongous amount of computational effort that goes into it. For example, for the homogenized constitutive law that takes fracture damage into account that I developed with Aris and Charlie, we had to come up with clever time integration schemes, etc., to do constitutive updates. For the other big computational effort is in the direction of capturing explicit fractures. And luckily there, thanks to Paul, actually, we have a long-running collaboration with the Los Alamos group, who have been developing for a long time finite element tools, essentially. You can think about it a la Zhu and Needleman back in '95, of putting cohesive elements between two finite elements, but much more elaborate. And what I have done with students, of course, is essentially repurpose their work, and they were interested in some non-earthquake problems, let me put it that way. We just repurpose that to earthquake problems. Third big computational effort on our end is on doing earthquake cycles. And that meant we developed, we didn't develop, we essentially borrowed ideas from, for example, gravitational physics on n-body problems to use fast multipole methods to do earthquake cycles. It's a way to accelerate boundary element methods. More recently, we are using hierarchical matrices, which is a generalized description of fast multipole methods.
Okay, thank you.
Yeah.
Thank you, and congratulations again, Harsha. Thank you, Alex.
Thank you very much, Jimedo. Okay, so now we will start the questions by the 3 examiners. So we will start with the one who woke up the earliest today, Ares.
Thank you very much, Alex. First of all, let me again congratulate Harsha for a wonderful presentation, and a presentation that actually showed very clearly the breadth of Harsha's involvement in a number of issues associated with the subject. It's very impressive to see somebody who can speak as comfortably about theory, about numerics, about experiments, and about observational studies. So this is very rare, and I would like to congratulate you, Harsha. Usually we are only experimentalists, only theorists, or only numerical analysts, or only observational scientists. You have combined this very effectively. When I started thinking about questions a few days ago, I panicked because having been associated with you for so many years and being your collaborator in many of the things that you presented today, I thought, oh, well, I don't have any questions anymore. I agree with him. So it is difficult to actually formulate questions, but well, I managed to come up with a few things that I wanted to ask you to elaborate on. The first thing has to do with an issue that you are clearly associated with, and the issue of the Rayleigh fronts that you have promoted throughout your career. And the question is the following. I wanted you to say a few things about the difference between the classical shear Mach fronts and the Rayleigh fronts in relation to what is happening to the free surface. What are the differences in out-of-plane displacement caused by the point of intersection of the shear front and then the Rayleigh front, which is at a slightly different angle? Is there out-of-plane displacement associated with the shear front itself, in addition to what clearly you have shown that exists because of the Rayleigh front? And what happens in the middle?
Very, very good questions. The best way to answer this is as follows. If I were to think again from in a singular elastic world, okay, where the crack tip is a point or a vertical line, if you like, then I have two nice planes that sheets, if you like, that are associated with the Mach front. And here, the motion, if you were riding along the Mach front, or if a Mach front swept by you, the motion is parallel, purely parallel to the shock front, to the shear shock front, okay? And that's it. And then comes the Rayleigh front. And now in between the shear and the Rayleigh Mach front, things are messy because you have dilatational field, you have motion associated with the P waves, if you like. You have motions associated with the S wave, but you have no motions associated with the surface waves yet, okay? Because it's outside the shock. And then comes the Rayleigh shock front. The Rayleigh shock front, as seismologists usually think about it, it's a complex combination of P and S, if you like. I tend to think like a solid mechanician. It's a police that ensures traction-free boundary condition is never violated. And the Rayleigh Mach front, naturally, because it's a complex combination of P and S, will carry a lot of vertical motion with it, much more, at least, than the shear Mach front. Now, having said that, now if we get into more realistic descriptions of rupture, where there's a cohesive zone, and it's not a point singularity at the tip, then everything gets smeared out, because every point along your breakdown zone, at least within your cohesive zone, is strongly emanating Rayleigh and shear Mach fronts. And if you look at it from the perspective of a synthetic seismogram, as Eric and I have done, it's impossible to distinguish, to make a clear separation between a shear Mach front and a Rayleigh Mach front, because they're all sitting on top of each other. What is certain is that there is a lot of vertical ground motion that is carried quite further away by the Mach front. And there, it's natural to assume that all the heavy lifting is done by the Rayleigh Mach front.
Thank you very much. So, this is actually a very interesting story here, and it is related to the latter part of your work related to tsunamis, because this is a surface effect that activates the normal motion. Now, on a different issue, in some of our experiments at Caltech, we have seen that even if you looked very closely to this, to the shape of the shock waves, some of them were curved.
Yes.
They were not exactly straight lines as the idealized linear elastic theory showed. How would you explain the curving of these shock waves?
I don't recall if we actually shared it with you, RS, but you know, that blackboard I showed, Mike and I went down this rabbit hole. And I've added, I never published those. I had those as handwritten notes, but I put them in the thesis as somewhere in the chapter. But here's what happens. If the linear straight Mach fronts are associated with the rupture going at constant velocity on a straight fault, mind you. If the rupture is accelerating on a straight fault, you would get Mach fronts that are concaving. And if a rupture is decelerating, you would get Mach fronts that are convexing. And if all of this is happening on a non-planar fault, okay, you get a very, very complex picture of a Mach front. In fact, that's on the cover of my thesis, some of the images I made, where for on a rough fault or for a fault that suddenly decides to kink. And now, one beautiful thing about Mach fronts, please bear with me for a minute here, is that, and this was why Mike and I went down that rabbit hole, is that say you did manage to image a Mach front, okay, image it spatially, and you got one snapshot of it. Now, the beauty of it is the Mach front has the full history of the rupture up to that point, which means that the local Mach angle is directly related to the rupture velocity from a point on the fault where the shear wave front went and became tangential to the Mach front. So I don't know, in the future or in a very nice dense array, if you could actually image the Mach front, you would have a detailed rupture velocity history from one snapshot. That's one of the beauties of Mach fronts. But our images were too poor at that time. You know, now you have better cameras, so maybe you have better luck this time.
Oh, absolutely. And the surprising, I think this is a very nice explanation. But also, though, there are cases in which the crack speed is extremely constant and they are curved Mach fronts. Could you think of another explanation that would give curving of Mach cranks in the presence of absolutely constant speed?
Well, the only other candidate that comes to mind is the other assumption that went into all the statements I made before was the material was rate independent,
absolutely, yes,
linear elastic, etc. Mach fronts carry humongous strain rates with them. So if you had a material that was rate dependent, like a viscoelastic material or plastic or whatever is your flavor, then you will have local changes in elastic properties, wave speeds, which will locally change the tangent angle and hence the Mach angle.
Exactly. And so that brings me to my third question, actually. Indeed, actually, because many of the experiments are done in polymers, but also rocks are known to be dispersive in some sense. You may have curving in the absence of varying speed. And that brings me to the Wu experiment that you mentioned at the beginning. According to the Wu experiment, there were cracks that were obtained to propagate at 1.1 times the shear wave speed with constant speeds if I remember from you,
Mm.
for about, for more than 10 centimeters. So scaling this up, that would be in there 10 kilometers. And perhaps more because that curve was continuing. So 1.1 times the shear wave speed is in the unstable regime.
Mm-hmm.
It's clearly in the unstable regime. And we have seen, both in numerical simulations and in the experiments, that this unstable regime only takes a few microseconds, as you pointed out. So there is a
Yes.
there is a conundrum here. Are those really super shear? Or is it that we have locally much higher, not much higher, higher wave speeds in the thermoset polymer that Wu is using? And really what he's observing is a constant speed at the local Rayleigh wave speed and not true super shear.
It's a possibility. I don't know too much about Columbia resin, so I can't comment on that. So first, let me start with the theory. Okay, everything I said. Under what conditions is it actually true? It's valid before reflections from boundaries, etc., come and impinge on the interface. It's valid under uniform initial state of tractions on the fault. It's valid under the conditions of uniform frictional properties. And I wouldn't be surprised if one or all of these are violated. The notion about stable being greater than square root of 2 is won't be a strong statement anymore. The second thing to keep in mind is the Wu's experiments. I would take that number 1.1 CS with a grain of salt. And this is an issue in numerical modeling as well, or theoretical modeling, is when you compute, or observations for that matter, you're computing rupture velocity. How? By actually finding the slope of a curve made up of discrete points along the xt plane. Okay. Good luck when trying to get rupture velocity when you are trying to split hairs on the speed regime. Wu's experiments were done on, he was recording them on pretty large strain gauges. They were a bit far away from the fault. And this was a time when you would take you would get literal images of the oscilloscope, which he has published in the paper, and then try to get the xt curve out of it. The point being that there could be several sources of error in measuring the precise position of the rupture tip, that I wouldn't myself get married to the fact that Wu saw something go at 1.1 times the shear wave speed. I was only mentioning Wu to be chronologically and historically accurate. That's about it.
No, that's
and
understood.
Like you said, that could it be locally really because of the fact that the material properties themselves are dynamically changing? Yes, very much so.
No, it is the constancy of that speed that makes me suspicious of this. Over long periods of time. So because things are known to be at constant speeds at Rayleigh wave speeds. It's an attractor. The Rayleigh wave speed is. But anyway, my last question has to do with experiments as well. But from your accumulated wisdom, what would you like to see as the ideal experiment going forward in the question of super shear? And that's a question for both you and Alex.
I think the piece of discussion we had earlier with Michel, etc., and with Paul. When you have faults are naturally heterogeneous. They have heterogeneous traction. Some may even argue it has some sort of self-similar, self-affine traction and strength distribution. It's not a alien concept coming from solids. So when you have a heterogeneous distribution of strength and traction, some of which are amenable for supershear transitions using the theory we have developed for under uniform conditions, some of which are not. What happens when a rupture tries to navigate its way through it? Does it just give up and say, let's remain subshear or sub-Rayleigh? Or do conditions emerge that things actually will go super shear? Because it's not so intuitive, because anytime you have these little barriers for ruptures, you are locally storing energy. The rupture may not propagate, but you are locally storing energy. So it may work in the favor of super shear transition. I mentioned Dunham's paper before, but that could be the case as well. So it's not a trivial answer, and it might go a long way into explaining why large super shear earthquakes are rare. And it may also go to explain, address the question of, do we have tons of tiny super shear earthquakes all the time? They just are not observed. That, I think, would be a neat question to address, because that's where we are at.
So maybe, Alex, we should do it.
Oh, you do it.
So, well, thank you very much. Those are my questions. And I would like again to congratulate you for a very, very nice talk and a very illuminating expose of the whole subject. It has been a great pleasure.
Thank you very much, Harsha. So at last, but not the least, our dear friend Shamita from Oxford. You're muted, Shamita.
You are muted. Yeah.
I can unmute you.
Okay.
I've already interfered with everybody else's, so I don't want to say too much, but of course I want to congratulate Harsha for a brilliant, brilliant presentation. And it was very nostalgic for me, because you took me from the beginning of my career to today. And you covered 40-something years in this.
I think I told this
very nostalgic.
Others don't know is I should have done this a long time ago, and it's going to be a mandatory reading. I actually, thanks to the confinement due to Corona, I read Shamita's thesis finally from front to back. And I'm not trying to massage the jury member. It was mind-blowing to see how much was done actually in that. So it was absolutely natural to go from alpha all the way up to omega, Shamita.
But I wanted to say actually the other way around. I was going to say, after all these years, every day the more educated I get, the more I realize how little we know. And we found many, 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 many problems. You know, I felt a little bit, you know, Michelle had some brilliant questions, you know, and I was actually wondering if some of the questions that Michelle was asking was related to this question that Aris just asked. Could it be that Rayleigh-Mac front is causing something which is causing those off-fault dip-slip faults?
Yes, in my work with Eric, where we proved the existence of Mach fronts, we ran a hypothetical scenario on southern San Andreas, and computed dynamic Coulomb stress change associated with these shear and Rayleigh mark fronts. And I should put the caveat emptor that we can't tell the difference anymore between shear and Rayleigh mark. They are fused.
It's the ground motion that I'm interested in that area. So it doesn't matter if I can't separate them.
What I can do, what I can say for sure is that, for example, we could, the Coulomb stress changes were positive along the Sierra Madre thrust fault because of, and that was quite far away, as you know. So you can have activation of dip slip structures for sure. This has to be done in a much more careful and more elaborate way to in the case of Kunlun, for example, where you have a vertical fault, a dipping fault, both of them quite likely meeting at depth. It's a very much more interesting question as to how the rupture decided to partition its way and how it managed to what speed regimes it took, et cetera, et cetera. Yeah.
And also ISMIT is another candidate for this modeling.
Yes.
I really liked figures, 2.34 and 2.36 and all those, because they reminded me of the real story for Kunlun, for example.
Yes.
They were really
very nice. I need to pull it up. I don't remember.
You have your thesis in your hand.
Yes, I do here right now. So
2.34, 2.36, really nice.
One sec. 2.34.
Doesn't matter. It's you can look later.
Okay.
Okay. So I was going to say that, in theses like this in the past, I saw that there was a section at the end giving some ideas of future work. Now you give us many, many examples, but you didn't write anything in your thesis. That section is not there.
So at least with ENS, I need to actually submit a separate document. That is my 5-year research plan proposal, which is not part of the thesis. It's not
okay. Are you going to send it to us anyway, just for?
Yes, it's just my ERC project. I have nothing else to do.
Oh, okay, fantastic. I also had a couple of small suggestions since you have so many tools at your hand. In the Pasleg et al. Paper, the 2013 paper, you did a section at the end on numerical modeling of that situation. Remember that?
Yes.
Numerical modeling
you're talking about
at the end of the paper?
Yes, the
slip pulse paper 2013.
Yes. It's a analytical slip pulse model of a steady state.
Yeah, but I was going to say, but it was also in 2D.
Yes.
But you have so many tools at hand. It would be really nice to do that in a fully 3D, I would really like to see that result for that particular case of Pasleg et al. In 3D.
So the whole, all I've done so far has been in 2D to set up proofs of concept, which is what I eventually went to the European Commission to get the project. So everything is moving to 3D.
Good.
And this whole business, one thing I'd like to do is really simulate this entire sample that Alex loves crushing, and actually model the fractures, acoustic emissions.
And the theoretical seismograms.
And of course,
I would like to see the seismograms. Because I felt all along that what we have so many tools, but what we are, and Michelle might agree with me, what we are don't have good enough still is data, Michelle. The data is still very poor.
Yeah.
You have an earthquake, you have 12 to 15 seismograms at the right distance to study that earthquake. And you can't have too many, usually there aren't any local stations. you can't put the stations too close anyway because they'll get destroyed. So you're very, very limited in the data. And that's our problem. And what are you going to do can you suggest what we can do to improve this?
Gosh, I'm not a data guy as well, as you know.
But we cannot move without the data, isn't it?
Yes, though, people come up with clever techniques all the time. Case in point being what Martin Vallée did with Eric Dunham to identify super shear rupture from very far field. Is that my laptop?
I think it's
No, it's me, unfortunately.
By coming up with essentially a clever theoretical idea of look for super shear.
No, but the theory is the word I didn't want to hear. I want pure data.
They
lots of it.
Yeah. Well, I'll say the usual statement as everyone says, and then I'll get shut down by all the observational folks. We need to put more stations around the faults.
Yeah, we do. Actually, that's exactly what needs to be done.
Yeah, but people, things are moving. There are big, dense arrays.
This brilliant stuff that Michel did for Izmit was because of those local stations he got.
Yes.
Yeah, without it, we wouldn't know.
And who knows? In the future, this was a sort of a moonshot that Jean-Philippe had. RS worked on it too, I think, for a while. If you had images of a fixed location, satellite images, optical images of a fixed location around a fault every second, or I don't remember what their dream project was, you could do image correlation. People do it for statics anyway. Maybe not.
Yeah, we proposed geosynchronous satellites flying a camera and using digital image coloration and looking at a big part of, say, of the San Andreas Fault and waiting and continuously recording till one day it ruptures, illuminated by white light, either sun or moon, but NASA did not buy it.
You want to sit only above the San Andreas.
Just to comment.
Because you
and just continuously look and dump the data till one day there is a signal saying, keep the data. And use digital image coloration, which is a technique that I developed in my lab recently. And we did the experiments with digital image coloration in the lab to show the feasibility. But anyway, NASA in its wisdom did not approve the mission, but maybe we can go to ESA that's a bit more progressive.
My friends are sending me chat messages. Of course, why satellites now tethered drones with cameras do DIC. I'm sure this is coming. It's a matter of waiting.
There is also DAS, huh? The fiber.
Yes.
Fiber.
I would like to make just one comment relative to what Harsha and what Shamita said, because it has to do with the history of accelerometric measurements. We have to remember, and the sparsity of accelerometers around fault comes from a large part because accelerometers were financed by earthquake engineers and set up by earthquake engineers. And earthquake engineers did not care having a very fine network. But I remember when I was a student, there was a big project at NSF, which was set up by the seismologists studying the source. It was to put to put the accelerometers not sparsely, but to create bigger rates of accelerometers. Indeed, if we look back at the role of the Imperial Valley earthquake, 1979, why did Ralph was Ralph able to see even in a small part of the segment, about 5 kilometers long, Supérieure speed? It's because so far, up to this day, it's the only relatively large earthquake which was recorded by an array. There was an array present there. Coincidental. But so we are still working with accelerometers for strong ground motion. And we are still carrying the problem of accelerometers being put by earthquake engineers, not by seismologists.
Yes, and actually your Izmit and Dusche, you have got those accelerometers, which is why you were able to see the Supérieure, remember?
Yeah.
Okay, I don't have a lot more to say, but I just wanted to say that, you know, you've done a lot of numerical modeling, Harsha. And one of the things is that I was wondering, how do you test your numerical methods? Do you have some data or some models or something to test it against when you use it?
So first of all, the numerical methods I use are well established, and their properties are well known in terms of convergence of solutions, etc. That's
but for a rupturing fault.
yes. I mean, there are several tests one can do. One, you can do cross-validation with other codes.
Yes, but that's our other codes. So I wanted to give you a couple of solutions that you could test complicated results, some results, before you use them in more complicated. You know that many, many years ago, Demovska and Kostrov wrote a paper. The title was A Shearing Crack in Semi-Space Under Plane Strain Conditions.
Yes, yes.
It's an analytical solution.
Yes.
For a dipping fault.
Yes.
Why don't you test your numerical method against that?
Sure.
That's one.
That's a good point. Yeah.
Another one is the Kostrov 74.
Yes, the classic one. Yes.
Crack propagation at variable velocity. So if you can model a real fault, because I think he does his variable velocity is a curve, some kind of a curve. You can take a real earthquake, fit a curve to it, and put that expression into that expressions, and you can do it. You can test your program then.
Yes.
Against
the tool that we used with Eric Dunham is actually meant for that, because normally the rupture velocity is part of the solution, but in some tools we drag the rupture front at the speed that we decide.
But it'll test some. It won't be a perfect test, but it'll test some aspects of the thing.
Sure.
Your thesis is so good that I couldn't find anything to criticize. So I worked very, 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 very hard, and I found a little one.
Perfect.
Okay. You know, you have this habit of referring to some work and putting a reference next to it. So you refer to Aristotle and you put next to it 1999. Sorry. Aris should give you you refer to Aristotle's theory of earthquakes and you put reference 1999, somebody's paper.
That must
I would like to suggest that Aris give you the original one. And then you can write for a recent review, see this paper of 1999.
No,
Another one, I'll give you another one. Another one was, oh yeah, the beginning of plate tectonics. And the reference is 2006. I'll send you a list of these.
I'm not surprised.
So, but you see the problem is that some people who read it don't realize that they think that that's when it happened.
Okay.
Yes, I actually, this is not a joke. I actually saw a student. Aris doesn't remember, even though he was there. We were all at Eriche. And this guy stood up and showed, I won't tell you whose student it was, but this guy stood up and put up the intensity map for the 1906 California earthquake. And the reference was his own supervisor, 1999. That picture, which is in Reed's book of 1906.
I see.
So I wanted to avoid that kind of thing. So I think I make a point of this to put in and maybe Aris can give you the reference for Aristotle, the original one. Okay, I've said
It
enough.
was 1999, actually.
Huh?
I'm joking.
It's a typo. No, sorry about that, but I actually went and skimmed through the English translation of it so that I was sure I was not saying nonsense. And it's cited as 350 BC.
Yeah, but but you didn't
put in my text somewhere. That's all. I know Aristotle didn't write it in.
No, but in your paper, in your thesis, you referred to 1999.
Okay. That's a mistake on my end.
Okay, and I found 2 or 3 others, so I'm sending you separately. Okay.
Yes.
Okay. Thank you.
Thank you, Shamita.
Thank you very much, Shamita. So your office is next to mine, my friend Harsha. So I won't dare ask you a question that actually generally it's the other way around. You keep asking me questions that I never can answer. And when I ask questions to you, I sometimes often have a hard time following up because you go so fast. One of the things that I just want to say that, it's been a blessing for me, for a number of students in this institution, that you came to France and that you joined the laboratory now it's been 4 years already, 5 years. And it's actually not to make a very subtle or not so subtle and very geeky joke, but it's been quite amazing to see your Supérieure transition. and in the last 5 years, right now you have it's been an energetic problem, as you showed it for a long time, where you kept putting in all these applications, in particular in the French system, which is not so compliant. When you don't know the weak path, but I am extremely happy, and I think I can sincerely say that when I learned last year that you got the ERC, I think I was more happy than actually when I learned I got mine. So I'm extremely happy for you. It's been really a blessing, and and you're one of the reasons. It's a daily enjoyment to come to work. All those cigarettes we share in the post-COVID world, on those, all these ideas. In terms of things that I hope we will end up managing to do in the next years together, is really this endless putting, not an end, but putting a stone, a small stone, on this endless conversation we have on deep earthquakes that we've started, I think, 6 or 7 years ago, discussing about that with Shamita also, etc. And I think there is a and you know, deep earthquake often goes super shear. There is the observation of Zhongwen, but there was also all the observation of Keiko Kuge, almost 10 or 15 years ago, where she showed that there was a number of deep earthquakes that actually were going extremely fast, and at that time she didn't dare saying super shear. Well, and since there is, even at this late hour, there is such an amazingly prestigious audience who kept actually aware, I think it would be reasonable to ask if anybody in the audience has also some questions for Harsha. Myself, I just want to thank you once again and to congratulate you and for all you did.
Thank you.
So anybody in the audience has a question for Harsha?
I won't take it personally.
Okay, if not, then maybe the easiest question, can you create a separate room?
Yeah.
So you can assign the jury members and myself to a separate room, and we will. There is intense suspense. Is he going to get it? Huh? I mean, I don't know.
Will it be on the same Zoom or you will...
Okay, well, thank you for the rest of the crowd for staying. Thanks for everyone else who have come. And I will close the session now. And
Dr. Harsha Bhat. Let's make it a little bit formal. So it's with great pleasure and honor that this amazing jury that you have been able to gather around this topic of Supérieure earthquakes, clearly a jury of the most amazing experts in the field, have actually all agreed that your manuscript has an amazing quality and it should be published and made available to a larger audience. So this is an advice. You made a remarkable presentation that was pedagogical and that went through the history of the field, a thorough history of the field, with a very high quality of your illustrations and you showed us outstanding results which span theoretical, experimental, and observational breakthrough that were published in the most prestigious journals. There is absolutely no doubt that you are worth the title of the Habilitation de Diriger des Recherches de l'École Supérieure de Paris, PSL. Make it formal a bit more, and we congratulate you. So now you're not Dr. Harsha, you're Dr. Harsha Bhat.
Well, thank you, Alex, for these kind words. You guys know me well. I'm very, very uncomfortable to praise, but thank you. From the bottom of my heart, thank you, my dear friends, for being on the jury and giving me your comments, critiques, and praise. They're all equally welcome, and I thank you again from the bottom of my heart. Thank you, Alex, for being the president of the jury. Poor Alex didn't have a choice there. And it's very awkward
Harsha,
to do.
I will see you at the cricket match.
Yes, we'll see each other in September.
He's coming to London for the cricket.
One of the conditions
so
that
I kind of what do you say, told the jury that it was a pity that we couldn't meet in the real world today, but as soon as we can have your kickoff meeting and a final meeting of my ERC, we will extend our invitation and we will be most happy to host you for a few days in Paris, all of you. So
That goes without
really-
saying.
We will be delighted. We will be delighted.
Harsha, you got my email to stay with us after the cricket match.
There are several emails I haven't looked at in the past week, so I will forward them this weekend.
And listen, if India is in the World Cup, you have to consider coming for that as well.
Yes.
Sent you a message about that.
So one of the conditions that I have put about approving your thesis is that you organize a Supérieure meeting.
Yes.
It's a great
in a
idea.
in a very pleasant place of the world.
Recherches or Recherches.
Corsica, yeah.
Well, good
Fantastic.
conversation. I'm loath to making this EGU session. I'm more in favor of small,
Oh, yes.
style of
Yes,
thing.
yes.
Much
That's
better.
great. Yes.
Shamita said Carges. We should inquire whether we can.
Yes. It's,
yeah.
I actually inquired.
Yeah.
Aris,
There is a waiting list of 2
beach.
years. Yeah, exactly. Yeah. That's what
You
I
can
said.
I think
swim in the
Recherches is
sea.
easier to get into, Alex.
Excellent.
Erice?
Yes. You know who
Then
would,
we need
who would know
some Italian connection.
No, we
Actually-
need Italian. Carges is better. Yeah.
it is Shamita, but it's a 3-year waiting list.
What for
So Recherches is easier to get into, and Alex, I would start with Chris Marone.
Mhm.
Yes, Chris Marone.
That's a great idea. That's a great idea.
That's a good idea.
Unless you want the Greek islands.
Yes, that's another great possibility.
I'm here.
Greek islands, nobody can say no. So Greek islands is paradise. So which one? Which one?
Well, I have a house in one called Serifos that has a huge French contingency of people that of French people that have houses in
I see
Serifos
it.
as well. So it is half French speaking anyway.
No, but is there a place for a conference?
Or we can always find something on the beach.
Oh, I see.
No, of course they will.
That's a great idea, Aris.
We will let me think about it. But the Corsica one sounds as good.
It's very good. Because it's a school all set up with the staff who take care of everything.
Oh yes.
Yeah.
Harsha, it was really fantastic. And
fantastic.
as I was saying to the jury before, you took us down memory lane. It was not only Samita, but all of us, I think, who have worked with you in various times. And actually,
Aris,
we have met each other during those times. And I remember actually even being in the same car with Michelle and Samita going to Northern California for 6 hours speaking about Supérieure on a long route, whatever it was.
Thank me for it.
Central Valley.
Yeah.
Yeah, great memories.
So again, thank you, Alex, for a wonderful, you are a natural, I think. You should be doing those more often.
No.
No, but you put the human touch in it.
Thank you very much, Aris. I'm happy. Actually, it's the first HDR I'm a president of, so I'm very excited.
Oh, that's fabulous, Alex.
And I can tell you that people will have to twist my arm from now on to do it. But this is the kind of presidents we want, or the ones that need their arms twisted. The others that want the job, we don't want.
Exactly, it's always the case. You never want the person who wants the job. Yeah. Anyway, I think I'm going to go and have dinner.
Yeah, I think so too.
It won't be a dinner in Paris, but what to do?
Soon.
Excellent.
If only there were a Pope.
Okay, bye everyone. It's a pleasure.
Have a good evening.
Bye,
Relax.
Samita.
Relax.
Merci, Michele.
Cheers, Samita.
Thank
Bye.
you, Paul.
Bye.
Au revoir.
Talk to you soon, Aris.
Merci Jim, merci
Yes.
Jimedo, merci Michel.
Relax, Harsha, before you talk to me.
So Harsha, we're going to crack champagne for you tonight, okay?
Please do. Thank you. Yes.
Okay, bye bye.
Bye for now. Talk soon, guys.
Alex, take care.
Thank you, you too.
Michelle, Tomato,
Ciao.
Ares, great to see everybody.
Michel,
Take care.
Paul.
Bye-bye from Bye-bye from New Mexico.
Ciao.
Ciao, Ares.
Oh.